right, let's do that. That's right. Cool. Who said that? Okay. Well, Mike, you want to come up here? Okay, so we're going to start the Track C session on data science, I believe. We're going to talk about something pretty interesting, particularly to people who know R. How many people here are familiar with R? Wow, very good. Okay, so you're in the right place. How many people saw our application spotlight demo earlier? Cool. All right, very good. Oh, Thomas. Okay. So last time at the first Spark Summit, we showed something that was sort of mildly interesting, and it's all about how to do R at scale, but do it in such a way that the R data scientist doesn't have to learn MapReduce. So today, we're very pleased to talk about something that has sort of, we factored out a lot of the code into a library and an API called distributed DataFrame, right? And the goal of distributed frame is to simplify big data for the rest of us. And I include myself in that group of the rest of us. We have three major sections to this. I want to start out with talking about the motivation for it, and then jump it right into sort of a demo that runs around the features and the benefits of DDF per the design. Very quick introduction. I am the CEO and co-founder of Adatao. More recently, I was engineering director at Google, working on the Google Apps team. PhD Stanford, UC Berkeley undergraduate. And my particular expertise is in large-scale systems, okay? And I know enough machine learning to be dangerous. With me here is Mike, also co-founder of Adatao. Mike is a PhD UI/UC in computer science, and he knows a lot more machine learning than I do. More recently, Mike was, I should introduce Paco then. Mike was at Yahoo working on Hadoop 2.0, and we also have, the rest of our team is a very similar profile to us, essentially a bunch of people with advanced degrees, but very importantly, have also seen data and other systems operate at scale, okay? So to set the context for why we want to do something and sort of factor it out called distributed DataFrame, if you transport yourself back maybe 5, certainly 10 years ago, right, when we were all happy with the small data world, SQL, very well developed, RDBMS and so on, and there's a rich ecosystem of applications and UIs and so on top of it, and everybody was very happy, right? And that's, you know, our blissful happiness in the small data world. In the last 5 years, something else happened, right? Big bad data arrived, okay? And for engineers like us, we get very excited, right? There's a new toy, okay? There's completely new toy, little, you know, major storm coming up, and we can come up with all kinds of stuff, like a storm, or literally R Hadoop, MapReduce, and of course even Spark, right? And so from that point of view, we want to make it easier and more efficient for people like data scientists and data engineers and even business users to be able to take advantage of this new big data thing. And here we have, you know, we're in this conference, our knights in shining armor, Spark, and of course Shark, trying to do that task, and I think doing it pretty well. But in my view, that's still not quite there, right? Because, you know, you look at the code that you are dealing with, right? Of course, if you are all here experts, you know, like we've gotten reasonably competent with Spark, that's okay. But it's still a pretty big proposition to ask people who are used to thinking about database tables and say, well, now your table is partitioned into 1,000 pieces. And so you got to ship in something, a closure, to operate one row at a time. And then when you're done with that, combine it into some weird way, shuffle and all that. So that's a lot of stuff, right? And then it gets even more complicated, you know, functional programming, monoids, monads, and so on. And so a lot of people we talk to and say, why can't it be simpler? Okay, this is how simple it should be, right? If you're trying to model like a, what is that company, Zillow, right? You're trying to model house prices. Then essentially you say, well, I want to load the data, I want to throw away all the junk stuff, and then I want to try to predict, you know, price as a function of square footage, zip code, and so on and so forth. That's your thought process, right? Unfortunately, that translates to many more thousands of man hours coding it. And so I've been in this field a long time, and as engineers, I find that we have this tendency to look at the world from the bottom up, right? What we're capable of doing, and then we're going to, expose these affordances from the bottom up to the user. So what we have today are things like the Spark engine, which is, in my opinion, the best that has come so far, or general DAG engines, and then on top of that, we put various APIs. And then we say to our users, our customers, our data engineer, our data engineers say, come, okay, here it is, okay? But from the top down, they look at it and they say there's a gap, right? Again, that model I said earlier about looking at things like tables and I just want to feed into a machine learning algorithm. So DDF is intended to fill that gap with a top-down view, okay? And what I mean by that is much easier shown than told, all right? So, and so the goal then is to have DDF be that solution where, we return to this happiness, celebration, beautiful land, and everybody can be happy with big data as we were with small data. So if you can see the design principle around a DDF is essentially taking a lot of the wisdom, right? Just because big data came along doesn't mean we were stupid before, right? It's a new challenge, but there's a lot of wisdom from the RDBMS community, SQL, for example. One time it wasn't clear whether it was going to be SQL or Codicil. That's the right UI for querying data. Well, the last 30 years has sort of settled that argument. Same thing with R, right? R was, I believe, created as S at Bell Labs, and there's been 3-4 decades of iteration, developing a lot of idioms around data mining and machine learning to make it easier and easier for the R data science to think about how to manipulate data, how to actually do ETL inside things like R Studio, and then do the modeling, right? A lot of those idioms are very, very good for, I can speak for myself. I come from the big data side, the scale side, It's been really good for me to learn from. And of course, people like me bring the power and the speed of parallel computing, right? So if you combine all three things together, you will inevitably come out with something like what we call distributed data frame, DDF. And in fact, if you saw the the application demo that we showed this morning, which of course we're very proud of, it's so user-friendly. It has NLP layer on top, right? It's something we call smart query that you don't even need to know any programming to start interacting with the data, exploring the data. We built that on top of the DDF interface. And I want to share with you this DDF that allowed us to build that product so quickly, right? If we didn't have the DDF model and we try to reach down one layer below it, it would have taken us probably, 5 times the amount of time in terms of productivity. Certainly 5 and possibly 10 times. Okay, so the architecture of what you're about to see is, this mouse doesn't show, but essentially there's a DDF layer that sits right above Spark's RDDs, right? Or any other parallel data abstraction. And DDF's goal, as I said, is to present a table-like interface to the user of that API. And so on top of that, what we've done at Adatao is to build systems or products like P Analytics and P Insights on it. Okay, but for the most part, the demo today will show you a raw terminal Scala shell interface, so you can sort of actually playing with that API. So I believe we're about to go into that. The demo essentially is going to be a client. The client could be a web browser. It could be Scala shell, and even RStudio will show that as well. And we're talking to a cluster sitting in Amazon, 8 node by 8 cores. And we're going to use the same. How many people here, probably the majority of you, are already familiar with the airline data set, correct? How many people know the airline data set? Okay, cool. All right, I think given enough talks, maybe we're trying to get to 100% response. But essentially, it's a 12 gigabyte data set, 20 years worth of flight information in the continental US, about 123 million data rows, and we'll be working with that in real time. All right. Okay, why don't you drive? You want to stand there? All right. Okay, so we think of DDF as comprised of 6 pillars. So the first one is what I mentioned repeatedly, which is we want to give a table-like abstraction on top of big data and hide away even the slight complexity of RDDs, which you still have to think of as distributed. Okay, all right, that code can be seen. So what Mike is doing, okay, he's going to do some housekeeping. He's creating a DDF manager, okay, and it's a DDF manager connected to the Spark engine. Okay. Okay. So the idea is that DDF is an abstraction or API layer that might, be connected to any engine. But of course, Spark is the best engine to use today because of all the capabilities within it. And he's connecting the manager to our cluster. Okay. And then Mike is going to do a SQL command to create a table. Now this table is sitting in the cluster, okay, but we have a reference to it. Okay, select from airline, yeah, and so that's going through either Shark or Spark SQL and loading that. And as soon as that's loaded, now this takes a bit of time because he's reading from EC2 disks. Okay, so now we have a reference to that table. Now table, when I say now table, I mean interchangeably DDF, right? It is distributed data frame. Okay, how many rows? Okay, so when there's an API, there's an n row, and that's it, 124 million rows, okay. No map reduce, visible. Of course, there's a lot of map reduce happening underneath. How about columns? Okay, 8 columns. Get column names. All right, so that's our schema. Arrival delay, departure delay, carrier delay, weather delay, origin, airport, and day of week, as well as whether the flight was canceled or not. Cool, I can see that. All right, so what are we gonna do next? So because it's a table, okay, because it's a table, we ought to be able to do what with it? SQL, what are some SQL idioms that you can do with tables? You project and you filter, right? Okay, so yeah, let's do some projection. Okay, so we're gonna select a few columns, a couple of columns out of that. Okay, so when you want to do that, you should better say, I want to project these column names and be done with it. So arrival delay, departure delay, unique carrier. Okay, so again, a bunch of map reduces running in the cluster. And let's see how many rows it is. It ought to be 124 million rows. Okay, and it should be 3 columns. Cool, and what are the columns? Right, so you begin to get this, okay, it should really be this fluid, right? This is what I mean when how we're able to do all these things. We can write a system like P Analytics and P Insights in 5 or 10 times faster than we otherwise would with a lower level API. Okay, and Mike is going to the next idiom, filter. Okay, so you want to, this is sort of a select where, right? And he's going to select unique carrier equal to American Airlines. Okay. Okay, so now we should have fewer rows. Let's see how many of those flights are American Airlines. Cool, 1.5 million. 1.5 million flights are out of American Airlines, a little more than 10%. Okay, how about columns? Yeah, get column names. There should be arrival delay, departure delay, unique carrier, right? Table 3. I shouldn't tell them what to do. Just let them. Okay, cool. So now we have essentially 3 distributed data frames in the cluster. One that was projected from the main, and the other was filtered. What else can you do? Okay, so now that we have this table, we can start to inspect it. Okay, let's get 5 rows out of it. Okay, there you go. Right. And so you can actually do a lot of data analysis with just this interface. Of course, with P Insights, we can make it even more human accessible. But here you can already begin to have enough power to just work with the API directly and get insights out of this data. Okay, Mike is going to do a group by. Okay, so we're going to do average, right? Okay, cool. Okay, so we're doing. Again, you can think of this as a SQL statement, but essentially it's an abstraction that says I want to group all the rows by each carrier and then compute the average delay out of that. Okay? And again, that gets run in the cluster. Should be very fast. Okay, certainly at 124 million rows. Okay, let's see how many rows we have. That would be the number of unique carriers. 29. Okay, can we just look at the table? Okay, cool. So there should be a unique carrier and there's an AVG underscore delay. Let's see a few rows out of that. Okay, top, cool. Okay, we're gonna sort. Okay, we're gonna figure out what are the I think it's sort ascending, right? So, what are the least delayed airlines? Okay. So the top 10. Okay, so that is Hawaiian Airlines. They're so good they actually arrive early, right? And then the next, I believe, is Aloha Airlines. Okay, so like I said, you're already beginning to get pretty good insights out of these very simple API calls. All right, because it's a table. Next, we want to go further. Okay, we learned from R. So R has a lot of these idioms like get summary that tells you some basic statistics about the data set. Get 5 num, right? The various percentiles. And okay, go ahead. Okay, do the summary. And in the cluster, it's doing a lot of statistics, right, about the table, and it's coming back fairly quickly, right? So you see the mean, the sum, the standard deviation, even has the count of NAs, right? These are values that are null in the data, right? So the API is tolerant of that. Okay. Okay. So this is computing okay. Yeah, cool. So that was also very fast, right? As you know, computing medians and so on, quartiles can take some time. Okay. Okay, cool. So that gives you, of course, it's much richer, but in the interest of time, I'm not going to give you every possible API call. So the goal, the third pillar of this is allow people to really focus on MapReduce, and I'm sorry, focus on analytics and not MapReduce. So what you're seeing here is the entire data pipeline. Okay, you know what we used to think of as ETL last night. You know, do over 24 hours, and then going in and then building the model, and then when you're done with the model, you evaluate the model, and then you actually deliver or deploy that model. All of that can be done through this API very quickly. Okay. Oh, okay. So this is also very exciting, right? All of us in the room here know that RDDs are immutable. And there's very good reasons why it's immutable. I'm not going to get into that, right? But on the Spark mailing list, there's a lot of people who ask, you know, can't you make it a little bit mutable, right? So, but from the top down, not thinking about functional programming and the requirements of it or the rigor around it, it's a reasonable request for people to say, I've got a table and I can modify it. So what we've done is, for the DDF, we can make it, by default, it's not mutable, but if you want it to be mutable, you should say, I want it to be mutable. And so all the operations are going to be, you know, to the top layer, to the top view, you're making changes in place. Of course, underneath, we're still respecting the functional programming paradigm. So we actually swap RDDs underneath. Does that make sense? Okay, so what have you done? Okay, just set it. Okay, so Mike just counted the number of rows, which is 124 million rows. And there's an idiom, an R idiom called drop NAs, right? So any rows that has an A in it, I don't want to deal with it, right? That's part of data cleansing, right? So in one step. Okay, so now he's dropped all the rows, still within table 2. Okay? So little things like this really, really dramatically improve productivity, right? So I can think of this table and I said drop the NAs. And we're going to do okay, so you can see sorry, I should be pointing to your screen. The count of NA is 0, right? That proves that we've dropped all the NAs from table 2. Cool? All right, so next, okay. So I'm not going to do the prediction in the interest of time. Well, maybe you're going to do, okay. Next, we're going to show you the integration, smooth integration with machine learning. So given a table, I want to run, in this case, k-means on it. Should be very easy as well. Okay, so Mike is picking up k-means from the MLlib. Okay. And even there, we've made it very simple so that you can, you know, call. We care a lot about what the signatures look like, right? So here he is training k-means, right, which is clustering into 5 clusters and 3 iterations. Okay, this is going to take a little bit of time, maybe 5-6 seconds or so. But remember, this is 124 million rows undergoing k-means. So. Okay, and so that was done. Let's immediately predict, right? So remember, this model is now sitting in the cluster. So operationally, if you know how sort of how Yahoo or Google predicts, based on the user arriving and which ad they should see or which article they should see, normally this model has to be exported, through various mechanisms, sometimes email, to the production system, right? So, but with this, it's already sitting in the cluster, and we can start predicting against this immediately. So there's actually a crossover between what we tend to think of as pure analytics, but actually it's available for the transactional side as well. Okay, cool. So I don't know what 2 means. It's just cluster number 2. All right. So that allows you to marry, data and algorithms and get immediate intelligence from this. So that's the 4th pillar. The 5th pillar is, and this is really exciting, a lot of people on the Spark mailing list, right, say, I want to share RDDs, okay? And again, there are good reasons why RDDs aren't shareable yet, but DDFs aren't limited to those constraints. So what we've done is sort of on a server implementation basis, we can name DDFs. We can name this table, and once you name it, you get a URI out of it. Okay, very simple URI. The URI here is, the protocol is DDF : right, / Adatao. That's our particular namespace, and the date table is flight info. Okay, cool. So what can you do with that? Okay, so there's so Mike is about to do some magic. He's going to switch into an entirely different tool, RStudio. Hi, JJ, if you're watching. Okay. So Mike is doing, this is RStudio, running just as a client independently on his machine here. There's one library that we load that's called Adatao. You can see that up there, library Adatao. He's going to connect to the same cluster. Go ahead. And one magical line later, line 4, connect to flight info, and let's hope that it works. Okay, cool. Now let's look at the column names of that. Yeah, indeed, that is exactly the same table that he was working on. So I could be sitting in Hong Kong, working on his data set using a totally different tool. Okay, that number of rows. And then now that you're in the R environment, okay, of course, with the Adatao library, you can start doing a lot of R against this same data set. Okay, so origin equals SFO, so he filtered that. Okay. Okay, so he's this is a transformation, right? Meaning in this case, adding a new column to that same DDF, a column called delayed, and it's defined to be if arrival delay is greater than 20 minutes, then you are delayed. Otherwise, you're not. Okay. And okay, so you're not gonna go ahead and do the pie chart. Now, normally you would actually do a classification training, right? GLM on it, and you can actually do this, but we're going to save you a bit of time, and just trust me, it can be done. So here, Mike is just showing. Yep. So those are the delay flights, roughly 20% or so, maybe 25. No, actually no, about 12. And then others are not delayed. Okay, cool. Anything else in here? Okay, So there you saw something. That is actually, maybe I'm not too excited. I don't sound too excited, but this is really quite cool, okay, to be. And so finally, because it is an API, it doesn't care what engine language is underneath. So it's not like we have to ship our code into the cluster or Scala or something. The user doesn't really care. Now, so happens that we built it that you can ship our code into it, but that's not the main point. You can work in any language, R, Java. The API itself is a Java API. Okay, we thought long and hard about it. We decided it had to be Java. And sorry. Okay, so you can even have